Welcome to The Explainer. Today, we're cutting straight through the hype to look at the hard, physical reality of where AI and software engineering is actually heading. We're taking a journey right into the core of how software development is evolving, looking past those massive valuations and flashy headlines to understand the mechanics of what engineers actually need from AI to build reliable software. Let's get right into it.
Here is what we'll be covering today. 1. The anthropomorphism trap. 2. The problem of drift. 3. Natural language as assembly. 4. Unified memory hardware. 5. ASICs and frozen models. And finally, number 6. Reengaging with syntax.
All right, section 1. The anthropomorphism trap. We've got to start by addressing this massive disconnect between the popular narrative of artificial general intelligence and what's actually happening down on the code base. There's a fundamental misunderstanding going on right now, and honestly, it's largely driven by the words we choose to use.
Back in 1984, the legendary computer scientist Edsger Dijkstra famously said, "Can computers think is as meaningless as can submarines swim." I mean, that just brilliantly hits the nail on the head. Assigning human traits like reasoning or thinking to machines, it completely distracts us from their actual mechanical function. Just like a submarine navigates water mechanically, it doesn't swim like a fish. AI processes data mechanically. It doesn't actually think.
So the real issue here is that when frontier labs start optimizing for creative or human-like outputs just to hit these anthropomorphic benchmarks, they accidentally introduce a massive liability for strict software engineering. Because, let's be real, we don't need our code refactoring tools to have human-like creativity. We need them to be completely predictable. Which brings us to section 2, the problem of drift. This liability is exactly what leads to the core engineering antagonist we're talking about today, drift. It's basically the hidden tax that engineers are paying for using highly creative cloud models.
So what is drift exactly? It's what happens when you submit the exact same prompt today and then submit it again, say 3 weeks from now over similar data, and you get a wildly different, unpredictable outcome. Now, high creativity drift? Sure, that might be great if you're trying to write a poem or brainstorm some ideas. But it is an absolute disaster if you need reliable, repeatable code refactoring across a massive software project.
And it's crucial to understand where this instability actually comes from. It's not just the providers dialing up the reasoning parameters. If you're relying on a massive cloud model, you're constantly at the mercy of undocumented in-version upgrades or post-processing engine tweaks happening behind the scenes. Your baseline is literally shifting right under your feet. This completely breaks repeatability, and it's forcing a massive shift toward localized control.
Okay, section 3, natural language as assembly. Moving over to the software side, let's look at how our choice of prompting language actually multiplies this whole drift problem. We've all been told that talking to computers in plain English is the future, right? But from an engineering standpoint, that's incredibly problematic.
Think about plain English for what it really is in the AI era. It's a highly unstable assembly language. Human language is loose, it's ambiguous, it leaves tons of room for interpretation, kind of like a lawyer finding a loophole. Code syntax, on the other hand, is precise and structured with super low drift potential. Think of it like Fortran. If we want reliable outcomes, treating English as the final destination for programming is a total trap. When people suggest the developers should just disengage from syntax and rely on plain prose, they are inadvertently decoupling the developer's intent from the actual mechanical outcome. It's literally like writing a law and just crossing your fingers that the judge interprets your intent correctly every single time. To eliminate that ambiguity, engineers are realizing we desperately need to start coding our prompts. We need a precise syntax. And that leads right into section 4, unified memory hardware. Because to escape cloud drift and process these structured prompts reliably, engineers are bringing their models local. And doing that forces a really fascinating physical hardware pivot. Let's compare the paths here. On one side, you have the high-powered GPU path, things like the RTX 5000 or 6000 Ada. These are incredibly expensive, power-hungry cards meant for raw graphical rendering, costing thousands of euros and drawing massive power for maybe 32 to 48 gigs of VRAM. But on the other side, you have the unified memory path, devices like a Mac Mini or an NVIDIA Jetson Thor. These come in at a fraction of the cost, drawing way less power, but because they combine their memory pools, they can offer up to 128 gigs of unified memory. That means they can comfortably host massive 30 or even 70 billion parameter models completely locally. And the crazy part? Running highly capable, low-drift local models at just around 100 watts proves a massive point. You absolutely do not need a trillion-dollar data center to do serious software engineering.
You just need the right local architecture.
Which brings us to Section 5, ASICs and frozen models. See, unified memory is really just a stepping stone to the ultimate, inevitable hardware solution. The real disruption we're heading toward looks a whole lot like history repeating itself.
If we look back at the chronological hardware evolution in crypto mining, the pattern is super clear. In 2009, the CPU era, mining ran on general-purpose processors. By 2011, GPUs completely dominated the hash race. But from 2013 onward, it was the ASIC era. Application-specific integrated circuits locked in the algorithms forever. AI inference for software engineering is destined to follow this exact same path. We are heading straight for a model-in-a-box future. Imagine hardware that is physically locked to specific models, like a Talus chip running a Llama 3.1 8B model. By burning a highly optimized AI model directly into the silicon, you get extremely low latency and power consumption, but more importantly, you get zero hidden cloud upgrades. It creates absolute predictability over time, a totally frozen model. There's a great quote from the source material pointing out that the shortcoming of ASIC-based AI hardware, the fact that it has hard frozen models on it, is actually a huge strength in a world that simply runs more reliably on low drift. What the big frontier AI labs might call a limitation, a model you literally cannot upgrade because it's hardwired into the chip, engineers actually call stability. It completely eradicates cloud-based drift. Finally, Section 6, reengaging with syntax. So, the question is, how do we tie this highly predictable, frozen hardware back to our daily coding workflows? What does that day-to-day actually look like?
The future of reliable AI coding isn't about AI completely replacing architects or spitting out an entire codebase in one messy shot. Not at all. It's about structured workflows. Humans write the business logic, and local, predictable AI handles the tedious refactoring. We re-engage with strict syntax, like a prompting domain-specific language. We move to model-in-a-box localized hardware. We demand strict provenance, meaning no rebase-heavy workflows. Every AI commit is human-accountable in Git. And we use low-key directional validation workflows, sometimes called reverse vibe coding, just to ensure the AI is aiding, not overriding the engineer.
It's a simple but profound structured approach. Step 1, you build specific syntax-driven templates targeted at your frozen local model. Step 2, you run those AI outputs against a strict local validation baseline. And Step 3, you use a Git merge to guarantee 100% human-approved code provenance. By treating AI as a mechanical tool rather than some autonomous thinking agent, we regain control, measurability, and real safety in the software lifecycle. And that leaves us with a pretty massive question to ponder. We're watching all these multi-trillion-dollar cloud AI valuations this year, right? They're all based on subscription models and ever-evolving reasoning parameters. But if the reality of engineering actually demands a highly predictable, non-upgradable frozen model in a box, are those cloud valuations sustainable? Has the market actually priced in this quiet, inevitable shift toward local, predictable engineering? Because if it hasn't, the entire business model of those frontier labs might just be completely misaligned with reality. Thanks for tuning into The Explainer. Catch you on the next one.